recording now. Hi, everybody. Welcome back to Richard Bliles, Dr. Whatever, chemistry class. We are through traditional chemistry. Congratulations, you've reached a milestone. You now know everything that I know about chemistry. We have two more lectures in the syllabus. Both of them are nuclear chemistry, to give you sort of a taste of the difference between general chemistry and nuclear chemistry. It's more in the realm of physics than it is chemistry, honestly. But you should understand the difference. And we'll talk a little bit about policies and weapons and power. Many years ago, I was living with my good friends, the Tsippases. Costa Tsippas was a physics professor at MIT. He is sadly no longer with us. Very charismatic man. He was his field. He was a physics professor. His specific discipline was nuclear arms policy. He was the world's. He was America's top expert, a civilian expert on nuclear arms policy. So whenever something came up and the news people wanted a civilian perspective on it, a new SALT II treaty or something like that, he was the one that they went to. One day I come home and they used to have really well known. I mean, they used to have Nobel laureates and high power people. He would go to military conventions, and they do have military conventions, or at least they did back then. I assume they still do, where the generals from around the world would meet. So American generals and Russian generals, and all these people would have these conferences. And he met some of the most powerful people in the world, including General Mikhail Milstein, who also is no longer with us. And I come home one day, and the Tsippases are having dessert with General Mikhail Milstein. This is actually kind of a longer story than I'm telling you. This is the abbreviated version, but it actually happened. And they insisted that I come and have sponge cake and strawberries with General Mikhail Milstein of the Soviet Union, who was in charge of the defense of the entire, and of course that also dates it, because back then it was still the Soviet Union. But I sit down between Casa on one side and General Milstein on the other. This was shortly after the Chernobyl meltdown, which is the worst civilian, well, it was one of the top nuclear civilian nuclear accidents in history. And of course, there's just a plot of land in the Ukraine that is still unusable because of radioactive fallout. And General Milstein and my friend Costa were having this debate over the civilian use of nuclear technology, and Costa, of course, was pro-nuclear power. General Milstein, having been from the Soviet Union that suffered this meltdown, was anti. And I was just a graduate student. I was a kid. I was, what do I know? They're in the middle of the argument. I'm just sitting right in between them as they're arguing back and forth. And finally, General Milstein turns to me and he says, "So, Richard, what do you think about this?" And I think I'm out of my league. Anyway, it was a very interesting topic. Of course, I am. That was what circa 1990, I suppose. Um, and I knew it was very obvious that the harm that we had done to Mother Earth from our fossil fuel reliance on fossil fuels. And I'm a big advocate, not necessarily for nuclear power, but for diversity of power sources. And nuclear power is certainly could fit into that piece. In my humble opinion, we'll talk about why and how that works actually today, not today, but in the next couple of lectures. I originally scheduled 3 lectures for nuclear power. 2 is going to be plenty, so we will finish on time. And then we're going to have next week, so that's this week, we're going to finish the syllabus except for the 2 special topics. Next week, I think, Tuesday, a week from today, I'm going to teach you how to build your very own fission, fusion, fission bomb. The government will probably be watching. So that should be fun. I don't know if they'll let us know they're watching. Probably not. I'm probably just gonna watch, and then next thing I know, FBI is gonna be at my door. A week from Thursday, I think what I'm going to do is talk about my research project. I've been, we talked about the hydrogen bond some time ago. If you want, you can go back and review hydrogen bonding. I have always had questions about the hydrogen bond. These are questions that have been going on in my head for the last 4 decades. It'll give you sort of an insight into the mind of a scientist, the way our thought processes go when we're tasked with something. And I'm going to share some kind of exciting breakthrough news with you. News that likely will never be published. Well, no likely about it. It will never be published unless I write a book. And if I write a book, it's going to be laughed at by my colleagues. It will be the end of my professional career, which is kind of over anyway, so it doesn't matter. But it's about the only way I'll have to get the news out. I'm actually still continuing the research. Once you have a breakthrough, it's not like the research stops. And we'll talk about that too. But today we're talking about nuclear chemistry, and let's get started with that. That should be fun. We are not sharing. Why are we not sharing? Which means I need to do this. And I need to do this. Blop. And I need to do that. And I need to do this. Nuclear chemistry. First of all, let me make this very, very clear. It is nuclear chemistry. It is not nuclear chemistry. Has always driven me nuts. So yeah, nuclear chemistry. How is nuclear chemistry different from regular chemistry? I think is a good way to start. Do you recall when we started this fiasco off with Dalton's atomic theory? In Dalton's atomic theory, one of the 2 basic assumptions was that elements never change. Every reaction we've seen, everything we've done, based on the concept that once you have an element, once you have fluorine, it's fluorine. It's always fluorine. It's always going to be fluorine. And that's all it is. That is not the case in nuclear chemistry. In nuclear chemistry, that goes right out the window. When scientists like Marie Curie, and we've talked about her before, began working with radioisotopes. Radioisotopes are isotopes that listen to the mix. They listen to, classic rock and today's best music. No, that's not right. That's not right. As you recall, isotopes are elements of the same. There are three of the same. There are three, not necessarily three. They're the same elements. So what's an isotope? Let's just review this real quick. Isotopes have the same atomic number, but different atomic mass numbers. Okay, atomic mass is the average or mean atomic mass, the weighted mean atomic mass. But atomic mass is the number of protons plus the number of neutrons. We call that the atomic mass number. The atomic mass number, as opposed to the atomic mass number applies to one isotope of an element. For example, there is one element where the isotopes actually have unique names. The only element where the isotopes have unique names is hydrogen. By far, the most stable and common isotope of element is hydrogen 1. Now, as you recall, we put for an isotope the atomic mass number in the upper left-hand corner. We put the atomic number in the lower left-hand corner. And the atomic number is equal to the number of protons. So the atomic number is equal to the number of protons. The three isotopes of hydrogen are hydrogen, deuterium, and normally we do not write the atomic number. Because once you put hydrogen, the atomic number is 2. I'm going to show you why we'll actually put the atomic number for isotopes here very soon, and you'll see why that is. The third one is called tritium. Tritium. These are the three isotopes of hydrogen. They are all atomic number 1. They all have one and only one proton. But notice that if you subtract the number of protons from the atomic number, you will get the number of neutrons. So hydrogen has 0 neutrons. Deuterium has 1 neutron. Tritium has 2 neutrons. That's the difference between the three isotopes, just the number of neutrons are all hydrogen. So the traditional chemistry of all three of these isotopes is identical. But, and this is a big hairy but, they're different isotopes. And this is why elements like hydrogen, their atomic mass, their average atomic mass is not an atomic mass number. That's why the atomic mass of hydrogen is actually 1.0079, as memory serves. It's because even though vast majority of hydrogen is just hydrogen, there's still trace amounts of deuterium and tritium in naturally occurring hydrogen. And that throws off the average atomic weight. So the atomic weight is the weighted average, which means it's the sum of all of these isotopes weighted by the percentage of isotope in a naturally occurring source. A radioisotope is actually an element that decays. It's an element that deteriorates, it falls apart, it becomes something else. We're going to talk about one of these decay rates here in not actually just a few minutes, but this is something that's rather shocking. So if you have, for example, a sample of uranium somewhere in the basement, when I used to work in South Dakota at my university where I used to work, down in the basement, we had a uranium ore sample. Now, that's not nearly as dangerous as it might sound, but people know uranium is radioactive. We're going to talk about that here in just a minute. It's called a radioisotope, which means if you could, and this is the tough part, if you could purify the uranium out of it, I could purify the uranium out of it. I could get a sample of uranium salt of some kind. Wouldn't be able to make weapons grade uranium, but I could have gotten a sample of uranium if I so desired. But the thing is, if I had gotten some uranium out of that ore, and I set it in my chemical storage facilities, today, if they went and looked at it, they would discover that it has thorium in it. It would still have uranium, but it would be contaminated with thorium. That's because the uranium is decaying into thorium. That's the big difference. A radioisotope starts off as one element and becomes something else through a decay pathway. So how does it do that? How does it decay? Well, let's first talk about radiation. There are three types of radiation that we usually speak of. Actually, technically four. We've spoken of one previously. Actually, let's add that to there. Let's add that to. We've spoken before of the X-ray. The X-ray is a beam of neutrons. A neutron is not an element. It is a subatomic particle, so it does not have, there are no protons on a neutron, so it has atomic number 0, but neutrons do have mass. We've spoken of that before. It has a mass of 1, the same mass as a proton. There are alpha rays. The Greek alphabet, just like our alphabet, has uppercase and lowercase letters. So alpha kind of looks like this little, almost like a fish, except we're not going to finish the fin. Alpha is the lowest energy. I'm going to put dash line here because usually when I talk about radiation, we don't include X-rays. Alpha is the lowest energy radiation there is. It can be blocked with a single piece of paper. Unless you are David Banner, who for some reason is particularly susceptible to becoming large and green when he's exposed to alpha. It's not particularly harmful. That's because alpha radiation is actually a stream of helium particles. A fast-moving stream. You know, it's not that alpha radiation is completely harmless. It's just that it's the least harmless. Just a stream of fast-moving helium particles. Beta rays. You get beta rays from beta fish. That's a joke. They have nothing to do with fish. Beta rays are a fast-moving stream of electrons. We're assigning the number -1 to this. The atomic number is a -1, and we'll see why in a moment. Then we have gamma. By the way, I would put the neutrons in this list right about here. But gamma is basically just a burst of energy. Gamma radiation does not, well, it usually accompanies decay. It doesn't, rarely do radioisotopes just emit gamma. It's usually a combination. It's alpha with gamma or it's beta with gamma, but it's just basically pure energy. So we're not even going to put this down. In fact, it's usually just symbolized with the gamma. Here we have from low energy to the highest. Gamma is most dangerous. So while alpha can be stopped with a single piece of paper, beta rays can be stopped usually with bricks. If you have a layer or two of bricks, the beta rays will be blocked. Gamma requires lead. And in fact, when you have x-rays done, I'm sure that there's residual gamma radiation, which is why they leave you exposed right there in the room while everyone else runs out wearing lead aprons. So gamma radiation is just pure energy. Nuclear reactions, there are two types of nuclear reactions. We have fission and we have fusion. This is why England is actually far ahead of the US in nuclear technology. Because while we had a lot of protests and people did not, basically they were afraid of nuclear power. And, we should have been cautious. We are cautious, honestly. So I'm not going to say they were wrong, but I think those protesters probably hurt the environment by protesting too strongly, because we could have been less reliant on fossil fuels today if we had more nuclear power. England, while we were protesting nuclear power, England was busy perfecting the fission chips. Fission chips. It's like a joke. You're gonna miss my jokes. All right. Fission. Fission is the process of going from larger elements to smaller. So large elements falling apart, that's fission. These are elements breaking apart, such as, for example, now, we're going to look at our first nuclear reaction here. Excuse me, sorry about that. That was rude. Uranium is element number. If you want to play along, this is open up your periodical chart. Periodical. Uranium is element number 92. And here's something that's kind of fascinating. roughly 20% of the Earth's heat, probably a little less, but roughly 20% of the Earth's heat comes from radioactive decay of naturally occurring, actually, they have to be naturally occurring radioisotopes in the Earth's soil. 20%. We've been taught ever since elementary school that we get our heat from the sun, and we do. A vast majority of the heat comes from the sun, roughly 80%, which is letting us down today because it's a very cold and bitter day today. But 20% comes from radioactive decay. If it were not for radioactive decay, our planet would be too cold to support life. So there's a little bit of trivia for you. Uranium undergoes, and don't write this down. Uranium undergoes alpha decay. Okay? Now, here's why I tell you not to write this down. Anytime you see one of these symbols, that symbol is completely useless to us. Okay? Because it doesn't tell us anything. It's just a symbol, alpha. So whenever you see that, now you can start writing, because I'm going to erase the alpha. Anytime you see alpha or beta, replace it with what it actually is. Alpha decay means that it is losing a helium. Now, this is an alpha particle. The law of conservation of matter still holds. So here's how you do this. To figure out what the uranium becomes, just subtract. Because you take 4 away from 238 and you get 234. And here's why you might want to put atomic numbers down. Take 2 away from 92 and you get 90. Atomic number 90 is no longer uranium. It has changed into thorium. All right? This is your first nuclear reaction. Did I do that right? Uranium becomes thorium. Yes, it does. And of course, you also get a lot of energy. So the law of conservation of matter holds, and that's the key to balancing nuclear reactions. In fusion, you go from smaller to larger. This is the kind of a reaction that's occurring in the Earth's sun, in the sun, not the Earth's sun, but in the sun. The sun, and I've seen cartoons about this. You know, there's no air in space, and yet the sun is on fire. Why is that? Well, it's because it's not a traditional chemical fire. It's a nuclear fire. It's undergoing fusion, which means that you are taking a smaller element like hydrogen. And again, just add up those numbers. 1 plus 1 gives us 2. 1 plus 2 gives us 3. Oops, I did that backwards, didn't I? Sorry. My apologies, that was a mistake. Atomic mass number goes on top. Hydrogen is always 1, always, always, always. Atomic number 2 is helium. Plus energy. Lots of energy is given off. Kim, any questions so far? Okay. Now, I hear things like this. And being a thermodynamicist, my gears immediately start to whir. because here we have energy being given off as fission occurs, and we have energy given off as fusion occurs. And it bothers me to say, look, both of these processes, taking a nucleus and breaking it apart, we're taking two nuclei and forcing them together, both of them release energy. There has to be something wrong. Law of conservation of energy says, look, something has to happen here. Here's what happens. The larger the nucleus, the less stable it is. Okay, so uranium's nucleus is so large that it's just unstable. And that's why, as you go from large to slightly smaller, you're going from less stable to more stable. That's where that energy is coming from. All right. Very small, not very small, but smaller nuclei are more stable. But when you smash them together, you go from small to another more stable, larger isotope. So if we were to look at we're looking at a chart of nuclear stability. This is the stability of the nucleus. And I just realized I forgot to turn off my music. I apologize if you don't like the kind of music I listen to, because you just got a snootful. Anyway, and I also forgot to turn off my phone. Let me turn that off real quick. That's not good. That's bad. Okay. Beep. Okay. Versus the atomic number. We're going to start here at, well, there is no element number 0, but here's 1. So here's hydrogen. Somewhere out here is however high you want to go. I don't consider these new artificial elements as elements. They're creating them to test the physics of the periodic chart, but they're not practicable. They fall apart in fractions of a second. So it's not like you can make a compound out of them. So I don't really consider those new elements as elements, but somewhere over here we have roughly atomic number 100-ish. Atomic number 100 is fermium. Somewhere like that. And what you'll discover is you get a curve that looks something like this. Boy, is that a poorly drawn curve. Let me redraw that. Much sharper. That's better. Right up here at the most stable isotope, the most stable element for atomic stability, by the way, notice I'm looking at the periodic chart. This is why I don't have students memorize the periodic chart, because even if you happen to remember, you still double check. Is element atomic number 26. This is iron. Iron has The most stable isotope on the periodic, I'm sorry, not isotope, I keep saying that, has the most stable nucleus on the periodic chart. So anything larger than iron, you get energy out from fusion. Anything smaller than iron, you get energy out from fission. Iron, you just can't get energy out of it. It's already the most stable. This is why both fission and fusion releases energy. But I also want you to notice this. If you have fission, now fission means you're going from larger to smaller. Now, notice that in fission, the atomic number is going down. Oh, shoot, there I go again. Boy, I am just backwards today. Backwards is something my mother used to say. If you find that term offensive, feel free to let me know. I will gladly refund your money. But notice your atomic mass, your atomic number is decreasing in fission because you're going from larger to smaller. So as you go from larger to smaller, that means that you're going this way on this chart. The fission reaction will release this much energy. Now that looks deceptively small. Because that much energy is typically 1,000 times more than your typical chemical bomb, chemical release. So if you made a bomb from chemistry, it wouldn't even show up on this graph. So that's how much energy you get from a fission bomb. But notice that fusion, you're going from smaller to larger. So as you go from smaller to larger, you are releasing this much energy, which is far more than this. So fission reactions tend to release far more energy than fusion reactions. Okay. Any questions so far? Do me a favor, open your book to the periodical chart. Okay, I'm going to not say that anymore. I'm saying it as a joke. I really don't want to make it a habit. So open your book, please, to the periodic chart if you can. And we are going to go back and continue this decay. And remember, these decay naturally. And you can find these decay pathways through a variety of sources. So as you decay, as you undergo alpha decay, you are moving left on the periodic chart. As you go from uranium to thorium, and Kim has left us apparently to go and get her book. I think her enthusiasm is beginning to wane, and I don't blame her. It's okay. I love this stuff. Doesn't mean everybody does. But anyway, as you go from uranium to thorium, you're moving left on the periodic chart. These decay pathways can be found in a variety of sources. Thorium, and by the way, I'm not putting down beta rays with this. When you undergo beta, remember these decay pathways are also tend to release beta radiation. Not beta, gamma, gamma, gamma. We're not putting down gamma. Gamma radiation is energy associated with this. And actually, we'll talk a little bit about that too. Thorium then undergoes gamma decay, not gamma, beta decay. Thorium undergoes beta decay. Well, this is kind of interesting. Notice that beta decay has zero mass. So we're still going to have atomic mass number. And actually, I'm going to go back and correct this chart to put a zero up there, just make it a little more. So notice that we're still going to have something with atomic mass number 234. But what's our new atomic number? Well, what plus -1 equals 90? Well, that has to be element number 91. So we are still maintaining the law of conservation of matter. Go to your element, go to your periodic chart, and you see that it's palladium. It is element number 91. And let's talk about this a little bit. What is beta radiation? If you kind of think about it, I don't want to mess this up, so let's go over here. Suppose you have a proton. The proton has a positive charge, +1, right? So what's a neutron? Neutron has the same mass, but no charge. Now, I'm not going to say this is a cartoon. I'm not going to say this is the way it actually works. We are beyond my expertise at this point. But this is how I think about it. Maybe I'm right. Maybe I'm wrong. I don't know. But how do you go from a +1 to a 0? Well, suppose we add another particle with 0 mass and a -1 charge. What has 0 mass and -1 charge? An electron. 1 plus -1 equals 0. The mass doesn't change because the electron has no mass. Well, I mean, we talked about that before, as a negligible mass. So in a weird kind of a way, a neutron is kind of a neutron can be thought of, I'm not going to say it is, it can be thought of as kind of a proton with an electron on it. It's kind of a proton, but it has a negative charge attached to it. Take that negative charge away, what do you get? You get a neutron. So in beta decay, you take a negative charge away from a proton and you change the proton to a neutron. The mass doesn't change because this number up here is not the number of neutrons. It's the atomic mass number, and the atomic mass number is the number of protons plus the number of neutrons. So while your number of neutrons increases by 1, your number of protons decreases by 1. So the mass does not change. The mass remains the same. But now the identity of the element has changed because we've changed the number of protons. And remember, the identity of the element, an element is identified by the number of protons in the nucleus. All right? So we've changed the number of protons. That changes the identity of the element, not the mass of the element, not the isotope mass. Kim, you are definitely going to have to go back and recheck. I don't know. I saw you sent me a message, but I don't want to open it. You're going to want to go back and review that little section here. So this is why with beta decay, now you're moving to the right of the periodic chart. If you look at your periodic chart, we went from alpha decay from uranium to thorium, and notice that it skipped 2. Went from uranium to thorium. With beta decay, we go back 1. So we went from thorium backwards palladium. All right. These are the two pathways of radioactive decay. So now we're at palladium. And again, this is not something that people make up. This is naturally occurring. And I don't know what this does, so I have to look it up myself. Palladium will then undergo another beta decay. And now you can do this in your sleep. With palladium, we still have 234. With beta decay, we go from 91 to 92. And look, we are back at uranium. But what's different? This uranium isotope is 234. We started with 238. I believe 238 is weapons uranium, if I'm not mistaken, but I might be wrong. Now, let's keep going here. And by the way, uranium naturally occurs in soil. I happen to know the state where Kim lives. And as it turns out, the state where Kim lives is very high in uranium in the soil. If you look at a map of the distribution of uranium, some regions of the country are naturally high in uranium, others are not. Where I'm at is kind of in the median, it's right in the middle. Kim's soil is very high in uranium. Well, uranium-234 also undergoes alpha decay, and let's remember this is alpha. This is beta. Well, now we are at thorium-230. We're going to go through this, although we're going to go faster and faster here. Thorium 230 undergoes alpha decay. Oops. And we're finally away from thorium. We're in element number 88, which is radium. And notice that each one of these steps, I just take the product from the previous to the reactant of the current. Radium, according to my source, undergoes alpha decay. Which means we go from 226 to 222, element number 86. If you look on the periodic chart, element number 86, double checking myself, is radon. Where have we heard radon before? If you have a house, have it checked for radon. Especially if you have a basement. What's really happening here, and this is where radon comes from, because we talk about radon as a hazard. It can cause all kinds of, well, it causes cancer and things like that. It's actually, radon is an inert gas. It is not reactive. It's not going to hurt you. Radon is perfectly safe if it stayed radon. And that's the key. It does not stay radon. So radon occurs from the decay pathway of uranium. It's a gas, which means it seeps into your house through any kind of a crack or opening. Isn't this normally the time we take a break? Okay, we're not going to take a break just yet. It seeps in. We're going to finish up this pathway, so it's going to be a very late break today. I hope that's okay. Is that okay with you, Kim? Of course, you also know she can leave. She has to. Anyway, it seeps into your home through cracks in the basement. Today, because it's a gas, of course, it's lighter than, it's floating around. Today, insulation is so tight that once gases get into your house, they have a hard time finding a way out. So if you have radon in your house, you want to know so that you can find the source of basically they look for cracks in the foundation, openings around pipes, like your incoming, your outgoing, your sewage pipe, basically. They look for things like that and they seal it up so that the radon cannot get into your house. They can't get rid of the radon, but they can stop it from coming in. And you don't have to worry about getting rid of radon, because radon undergoes further decay. And this undergoes alpha decay. To become element number 84. Polonium. So we undergo alpha decay to become polonium. Actually, let's just move this a little out here. Whoa, that was bad. Okay. My apologies. Trying to reorganize notes. And of course, this one has a circle around it, which you're not going to see because I just selected it instead of circling it. All right. So back here. So where were we at? Polonium 218. Polonium will undergo beta decay. And here is the real problem. Well, here's one of the problems. Astatine. Now you breathe in radium into your body, and the radium undergoes beta decay. And remember, beta decay is more dangerous than alpha decay. Now you're becoming irradiated from inside your body. Radiation attacks DNA, which causes mutations, which eventually causes things like cancer. This is why radon is so dangerous, not because you're having a reaction with radon, but because the radon continues to decay. We're going to keep going here because this keeps going. So now we're in a lot of danger because we are irradiating ourselves. Astatine, oops. this going quickly. Astatine then becomes bismuth. Bismuth undergoes beta decay. Once again becomes polonium. Did I do something wrong here? 83, bismuth. Oops, I did do something wrong. No, I didn't. Then polonium undergoes alpha decay. And look, now we're at lead. Lead is a heavy metal poisoning, and all of a sudden you have lead poisoning, not because you ate paint chips as a child, because I know that Kim has eaten paint chips as a child. There has to be an explanation. I'm kidding. Kim is a very good friend of mine. She's smiling. She knows I'm just kidding. But now all of a sudden you have heavy metal poisoning, not because you've been eating lead paint, but because you've been breathing radon. Which undergoes further decay to become mercury, which is also a heavy metal. And that's the end of it. The mercury is stable. The mercury will stay with you. But this is how you get radon into your house. Natural part of the radioactive decay. This is how the radon is harmful, not because the radon is so harmful, but because you're irradiating yourself from the inside and you're getting heavy metal poisoning. So yes, if you have a house, get it checked for radon. It's worth your peace of mind. I used to have a little radon detector, actually, back when I had Blia Laboratories, which was not successful because I refused to use scare tactics to get people to buy my services. But we used to be able to do that. Anyway, we're going to take a quick break. Kim, since we were so late, let's take a 7-minute break. What do you say we come back at 11:05? How does that sound?
Sounds great.
All right, we're on pause.